In today's video, we will discuss about the width of the central maximum and the secondary maximum in a diffraction pattern. For that, let me consider a slit. Let this be a slit of width, let's say some A units. This is the width of the slit and let it be A. And let's mark a point O at the center of the slit. See, this is actually, slit means an opening. This is the slit. And this is the midpoint of the slit. And let me take a screen, or let me keep a screen at a distance, let's say some D units from the slit. This length is D. And let me join this O and the screen, that is, this line is perpendicular to the screen. Now, we know a diffraction pattern is formed, or let this point be some A. Now, a diffraction pattern is formed symmetrically to the point A, that is on either side of the A. That is, see, this is a bright fringe and we usually call that as the central bright fringe, or called the central maxima. And this central maxima is symmetrical to both the sides of the point A. That is, this one is the central maxima. Central max or central maximum. It's usually the bright fringe. After the central maximum, a dark band is formed, and after that again a bright fringe is formed, like this. Similarly, beneath the point A, after a dark fringe, again a bright fringe is formed. This pattern continues like this. Okay. On either side of the point A. So, see, this is central maximum is actually the bright fringe. This one is the dark fringe. This is again the bright fringe, and after that a dark fringe. This pattern keeps on, this pattern continues on either side of the point A. Now, when I join the point O to here, and let me mark this angle as some theta, and we usually take this as the, let me take this distance as x, that is, this point is actually A. This distance x is called half the width of the central maximum. Okay, now actually I can say this point is, that is, let's mark this point as some B. This point B is on the dark fringe. And we know the condition for, or if I draw a graph, the intensity graph, it's usually called the intensity graph. See, in this region, we have the maximum intensity. So I can draw a graph with maximum amplitude. And this intensity keep on decreasing. At this point, we have a dark fringe. So the intensity is 0, or it coincides with this line, coincides with the screen. And again, the intensity is increasing because we have a bright fringe. After that, again a dark fringe. Okay. Again, we have a bright fringe. So this is the intensity graph. Okay, when I draw it horizontally, I'll get somewhat like this. The intensity keep on decreasing on either sides. Clear? So this point B is on the dark fringe. And we know the condition for the dark fringe. Condition for the dark fringe in diffraction is actually A sin theta is equal to n lambda. where lambda stands for the wavelength and sine theta is the sine of this angle theta. But we know this is the first minima. So we have n is equal to 1 and we have the angle is very small. So sine theta approximately equal to theta. That is for small angles. For small angles. Now substituting these two in here, I'll get a theta instead of sine theta. I can put theta is equal to 1 into lambda. Or I can write a is equal to, theta is equal to lambda by a. Call that as equation number 1. Now when I take this triangle, let me see, this is point A. Let me draw this triangle again. This is O, this is the point A and this is the point B. We know this length is x, this angle is theta. See, this OA is approximately equal to OB. OA approximately equal to OB. Since this angle is very small, this angle is numerically less than 1 degree. Okay, so we can take OA approximately equal to OB and that is equal to the length D. Okay, D. Now since this angle is small, I can consider this as an arc. And we know the relation, angle is equal to arc length divided by radius. Okay, so that will give, we know angle is actually theta, arc length is actually x divided by, this is the radius. So radius is actually d by d. Therefore, x is equal to, I can write d theta. Now, if I plug in this value, that is, let me erase here. Now if I plug in the value of theta in this equation, I'll get x is equal to d into, instead of theta, I can write d lambda by a. So that will make only half the width of the central maximum. Actually, the width of the central maximum is this much, that is this length. And we know this length beta, this length is actually beta. So beta is equal to 2 times x, implies beta is equal to 2 into d lambda, since x is d lambda by a. So 2 d lambda by a. Let me mark that as b naught, since it is a central maximum. Okay, so this is the width of the central maximum. Clear? Now I need to find the width of the, see, this is the secondary maximum. Secondary maximum. Why is it so? Because we already have a central maximum. So this is the first brightest fringe. After that comes this one. So we call that as secondary maximum. Now I need to find the width of the secondary maximum. For that, let me join this point also. Okay, let me consider that as OB. Let this point be some C. This point is some C. Now, listen this part very carefully. When you look at the secondary maximum lies between, that is, see, this is the first minima, and this region is the second minima. Clearly, I can say the secondary maximum lies between the first minima, that is this one. That is, this one is the first minima, and the second minima. That is, this dark region is the first and second minima. So when I consider, see, let me take this time, this one as theta 1. See, before that I took that as theta. Now let me take this as theta 1. So the condition for, or let me draw this triangle again. Let me erase all this. That is this triangle, that is O, B, this one is B. Here we have C. Let this be theta 1 and let this be theta 2. And we know since it is the first minima, we generally have A sin theta is equal to n lambda is the condition for dark band or dark fringe. And for the first minima, we have A equal to, see, instead of sin theta, I can put theta. Here for the first minima, we have theta 1. For the first minima, we have theta 1 is equal to, n is equal to 1 for the first minima. For first minima n equal to 1 and theta equal to theta 1. So that I can write theta 1 is equal to lambda by A. Call that as equation number 1. And for the second minima, we have n is equal to 2, and I can write this equation as A, instead of sin theta, I can write theta 2 is equal to, here n is equal to 2 lambda. That means theta 2 is equal to 2 lambda by A. Call that as equation number 2. Now this angle, that is this angle, is the angular width of the secondary maxima. This is the angular width of the secondary maxima. So theta will be, from the figure itself, it is theta 2 minus theta 1. So 2 lambda by A minus lambda by A, that is equal to 2 lambda minus lambda by A, since the denominator is same. So we will get lambda by A. So let me mark this as theta dash. Okay, because we already took theta before, theta dash. So theta dash is equal to lambda by A. Now again I can use that formula we used before, that is angle is equal to arc length by radius. Here also we have OB approximately equal to OC equal to D. Since this length is very small, since this angle theta dash is very small, so this length and this length is approximately equal to D. Now again we have angle, that is theta dash is equal to arc length. This is arc length. Let me take that as beta. Arc length beta divided by the radius. Here the radius is OB or OC. So D. This is the arc length. This is the radius D. That will give beta is equal to theta dash into D. Beta is equal to, theta dash is actually lambda by A into D, or lambda D by A. So this is the expression for the width of the secondary maxima. Now we know the width of the central maxima. We already found that as beta 0 is equal to 2 lambda D by A, and we know the width of the secondary maxima is equal to lambda D by A. When I divide these two equations, I can cancel this lambda D by A and lambda D by A. So beta 0 by beta will be equal to 2. Implies beta 0 is equal to 2 beta. That means the width of the central maxima will be 2 times the width of the secondary maxima. Also, when you look at the equation for the width of the central maxima or secondary maxima, for instance, take the width of the central maxima. It is actually 2 lambda d by a. Clearly, you can see that beta 0 proportional to 1 by a. They are inversely proportional. So, when the width of the slit increases, the width of the central maxima decreases. Clear?